like we did for finite difference frequency domain, we're going to divide our discussion of rigorous coupled wave analysis in 3 sections, or 3 lectures. The first one's the formulation. This is the one where we'll have equations flying all over the place. The second lecture, the lecture following this one, will be the implementation, where we try to bring peace and harmony to this, and it's step by step, do this, do this, do this, do this. And then the third lecture, a bunch of examples. And hopefully by the time we get through all of that, you'll have rigorous coupled wave analysis down just fine. Now, having been through the transfer matrix method and all the Fourier space Maxwell's equation stuff, I think you'll find rigorous coupled wave analysis quite a straightforward extension of what we learned. In fact, it's just a very simple generalization to what we learned with the transfer matrix method. I'll give you some background information that we'll need for the lecture. Then we're going to discuss Maxwell's equations in Fourier space, but in a slightly different form that we'll call semi-analytical form. And this will be very similar to what we did for transfer matrix method, where we leave the z derivative analytical, and we end up deriving a wave equation with that. And that'll be the next step. Then we're going to solve that. And in fact, once we get our matrix wave equation, the math here is literally identical to the transfer matrix method. In fact, I just copy and pasted from slides in that lecture to formulate things like scattering matrices, how you calculate transmitter reflection fields, etc. And then in the end, as an added bonus, I'm going to talk about something called the enhanced transmittance matrix approach. We talked a bit about what makes transfer matrix method blow up, and this was suffered by rigorous coupled wave analysis, and then the first time it was solved with a technique called the enhanced transmittance matrix approach. Now, I'm teaching scattering matrices because that seems to have won as the dominant way of cascading multiple layers. But there are a lot of benefits to other methods, specifically this one. It's about 10 times faster than scattering matrices in my experience. And I even have a pretty good formulation of scattering matrices that I think is a bit more efficient and runs faster than others, and I still notice a significant speed increase with the enhanced transmittance matrix approach, but it's more memory hungry, whereas the scattering matrix is a bit more memory efficient. So we'll get to that. Background. When we are using rigorous coupled wave analysis to model something, going way back to our first lecture, this is a great method for modeling things with low to moderate index contrast and periodic structures. So what we have on this slide is a periodic structure. And we'll notice in the x and y directions it's inhomogeneous and can be arbitrarily crazy in this method. But notice in the z direction it's sort of extruded in that direction. And we're going to divide up an arbitrary structure into a number of layers like this that are all uniform in the z direction. So if we pull a unit cell out from this lattice, it's uniform in the z direction, so we really only have to look at a cross section of this. So down here we have a cross section of our unit cell, and this really is representative of a 3-dimensional device that we're showing up here. But in rigorous coupled wave analysis, we're going to analyze the cross-section numerically on a grid like we're showing here, and then the longitudinal direction, we have an analytical solution exactly like what we did for the transfer matrix method. So here's the geometry and the best picture that I can come up with of numerically what's happening underneath the hood of rigorous coupled wave analysis. So our z-axis will point from top to bottom. Down here, what I'm showing is region 2. Other times we'll call this the transmission region. On the top of the device, region 1, or sometimes we call this the reflection region, or the incident region. This is where the applied wave is incident from, and also has some kind of polarization vector, has some elevation angle theta, and a radial angle phi. No matter what our device looks like, we divide it up into a series of layers. The thing about these layers is that they can be as complex as anything in the x and y directions, but in the z direction, each one of these layers is uniform. So if we have a curved device, what we'll need to do is divide it up into a whole bunch of layers and then approximate each of those layers being uniform in the z direction, albeit very thin, and that's called the staircase approximation. Now this is a Fourier space method, so in each one of these layers we're going to expand the field into a plane wave basis. So I sort of color coded it so the plane wave expansion, if you will, is the same color as the layer it's in. So we're going to have a separate plane wave expansion inside each of these layers. And in the z direction then we can propagate those analytically. We'll match boundary conditions of all these different plane waves at the interfaces, and when we're done we'll describe each of these layers with a scattering matrix so we can describe propagation through this entire stack. Unlike the transfer matrix method now, we can have inhomogeneities in the x and y direction, so we can take into account diffraction and other crazy things. In this formulation, we're going to adopt the e to the minus j beta z sign convention. We could just as easily have chosen the positive e to the positive j beta z, but the vast majority of the literature adopts this, so we're going to stick with that here. So we're going to repeat some of what we discussed in the lecture where we converted Maxwell's equations to Fourier space, because we're going to put these equations in just a slightly different form that we call semi-analytical form, and we're not going to Fourier transform the z coordinate. We will leave that analytical, but I think you'll follow the steps a lot more quickly now that we've been through the Fourier space lecture. So this should be a common starting point. We have Maxwell's equations, we've assumed isotropic materials, and we normalized the magnetic field by multiplying by the free space impedance, and we've also multiplied by minus j. Remember, that gives Maxwell's equations the symmetry that we're looking for. So this should be a very familiar starting point. Next, we will be looking at Maxwell's equations as if it is in the middle of what I call z-uniform media. Talked a little about this on a previous slide, but in the x and y directions, the unit cell can be very, very inhomogeneous. It could be anything. But we're talking about something that's extruded or uniform in the z direction. And when we're manipulating Maxwell's equations right now, we're right in the middle of this somewhere. So whatever the wave is in is uniform in the z direction, but it's potentially inhomogeneous, very inhomogeneous even, in the x and y directions. Given that we are in a z-uniform media, it's uniform in the z direction but periodic in the x and y directions. So, in terms of the materials, we're only going to Fourier transform, or we're only going to expand into a complex Fourier series in the x and y directions, not the z direction. And that's the big difference with what we did in the Maxwell's equations in Fourier space lecture. We transformed all coordinates. Here, we're leaving the z coordinate alone. So we have our two-dimensional Fourier series for mu and epsilon, and we also have equivalent two-dimensional Fourier series for the fields. And for square and rectangular symmetries, we will expand our wave vector, the transverse wave vector components this way. So we'll go to the first of Maxwell's equations, and we will take the expansions that we had on the previous slide and substitute them in, following exactly what we did in the Fourier space lecture, but we're leaving the z derivative a z derivative. So we work through the math, and here is where we end up. And of course we took a bunch of steps that we expanded on before and lumped it all in here. So here really is the final equation. We have this double summation here, which we'll remember is a convolution. And here we're convolving the permeability with the magnetic fields. Notice we're writing our z derivative now as an ordinary derivative because z is the only independent variable left. So the partial derivative becomes the ordinary derivative. Well, if we did the same procedure to all of these 6 Maxwell's equations, here where we would end up. And so I call these Maxwell's equations the semi-analytical form of Maxwell's equations in Fourier space. to be completely in Fourier space, we had minus jkz or something here multiplying this u, but now we have a z derivative that appears. Okay, so each one of those equations will be written once for every spatial harmonic in the expansion. And of course, this large set of equations we can put into matrix form. So this next section of notes is talking about how to do that. Before we do that, we are going to normalize our wave vector. We did this with the transfer matrix as well. So we'll take the actual wave vector component and divide by the free space wave number. So we have normalized kx, ky, and kz. We will also normalize the z coordinate. Now when we do that, we end up with these 6 equations, and notice that the k naught has disappeared. It didn't really disappear, it got absorbed into these normalized k terms as well as the derivative with respect to z, but it's no longer explicitly written. Okay, so we have one of these Maxwell's equations in semi-analytical Fourier space, if you will. We can jump immediately to that equation in matrix form. So remember, we are writing this equation for every possible combination of m and n. In other words, we're writing this once for every spatial harmonic in our expansion. That large set of equations we can write in matrix form this way. And the contents of these matrices shouldn't be very surprising. The first one is our ordinary K matrix. So in this case, K sub y, we have all the K sub y components for all the spatial harmonics running down the diagonal. Everything in the off diagonals is 0. So this really is a diagonal matrix and is a very sparse matrix. This bold U sub z is a column vector containing all the z components of the magnetic field for each one of our spatial harmonics. We have another U sub y, which is all the y components, and S sub x. These are the x component of the electric fields stored in a column vector for each one of the spatial harmonics. So remember, these are all the spatial harmonics inside this z uniform media that we're writing Maxwell's equations for. And then, of course, we have the derivative here. It's an ordinary derivative with the normalized z coordinate. And this epsilon is a convolution matrix. It's only performing a convolution in the xy plane. So going back to the plane wave expansion method notes or the Fourier space notes, this is just a two-dimensional convolution in Fourier space. And we can use the same codes we developed there to calculate that convolution matrix. Nothing needs to change. So if we step through that same argument for all of our 6 Maxwell's equations in this semi-analytical Fourier space, here's where we end up. Now this should start to look familiar to the equations that we had when we did transfer matrix method. One of the big difference now is that we have a bold K, which is a diagonal matrix instead of just a single scalar number. So we now have Maxwell's equations in the semi-analytical form written as matrices. Now we want to combine these and derive a matrix equation, wave equation. So here are our 6 equations that we had on a previous slide. We are going to solve the 3rd and the 6th equation for the longitudinal components, SZ and UZ. So when we do that, here's the 2 equations we get. And based on a lot of other lectures where we did similar things, you can bet you what we're going to do with this. We're going to take this expression for SZ and plug it into these 2 equations. And we'll take this expression for UZ and we'll plug it in up here. And then we'll end up with 4 equations without any longitudinal field components. No field components in the z direction, which we're calling the longitudinal direction. So here's where we do that. Again, we'll take the expression for S sub z and plug it in down here. We'll take this expression for UZ, plug it in up here, and we end up now with 4 equations not containing any longitudinal field components. There's no S sub z or U sub z in these equations, and we're down to 4. So now we'll just switch the order of these equations and rearrange terms so that these ordinary derivatives end up on the left side of the equal sign and everything else ends up on the right. So when we do that, we've just rearranged our 4 equations into this form. Now we're going to put these in block matrix form. So we'll take these first 2 equations from our previous slide, and we can write them in block matrix form this way. So out comes a matrix Q, which we've collected all these coefficients. It has our diagonal K matrices as well as our convolution matrices, epsilon and mu. We'll take the second set of 2, and we'll write it this way with this big ugly matrix P. We now have our PQ form. Our P and Q's look slightly different than they did for the transfer matrix method, but what you'll see is the differential equations that we have left look exactly like what we had for the transfer matrix method, and in fact, once we get to the PQ form, many different methods look exactly the same. In fact, this is no exception. So in the special case of P and Q in a homogeneous layer, it turns out, if you remember, the convolution matrix in a homogeneous material is just a diagonal matrix with the average value of that layer going down the diagonal. So our convolution matrices are identity matrices with a constant multiplying them. So in fact, for homogeneous layers, we don't have to construct convolution matrices, and in fact, it's best not to. And we calculate P and Q in homogeneous layers this way, where this mu and epsilon are not bolded, they're not convolution matrices, those are just scalar constants. Now we're in a good position to derive a matrix wave equation. So we'll start with equation 1 that has the P in it, and we'll take a derivative with respect to Z. We already have a first order Z derivative, so that becomes a second order Z derivative. P is not a function of Z, so in fact it comes to the outside of the Z derivative, but now notice we have the derivative multiplying the magnetic field components. Well, our second equation, which had Q in it, had an expression for the derivative of the magnetic field components. So instead of saying the derivative of the U's, it's just Q times the S's. So we'll take this expression, plug it in here, and here's where we end up. The second order derivative of the S's equals P times Q times the S's. So in fact, here we are at our matrix wave equation. This is, I think, the exact same thing that we wrote for the transfer matrix method. But now our omega squared is P times Q, and it looks a little bit different because it's built of larger matrices, but in the block matrix form, it looks the same. Now let's solve this, and if you followed everything in the transfer matrix method, everything here is a repeat, nothing's new. It's just we have larger matrices, but since we're writing these in block matrix form, there's nothing different. So here is our matrix wave equation, and we can solve this sort of pretending that these aren't even matrices or column vectors or anything, and we can write our solution this way. And we have the terms we remember from the transfer matrix method, where here's our forward propagating term, here's our backward propagating term, and this is our initial condition for the forward waves and our initial condition for the backward waves. So we have this exponential of minus omega z to worry about. Omega is no longer a diagonal matrix, so before we handled this very easily. Now we can't. But we have to calculate the exponential of this. So remember that the function of a matrix A is its eigenvectors times that function applied to the eigenvalue matrix, which is a diagonal matrix, and we can very easily do this to each term down the diagonal, divided by the eigenvector matrix again. Well, if we apply that to this exponential, here's where we end up. So W now is the eigenvector matrix of omega squared, and lambda squared is the eigenvalue matrix of omega squared. So we also have to take the square root of it. But we can convert our exponential, or we can come up with a matrix form of that exponential this way. So just remember, W are the eigenvectors of omega squared. Lambda squared are the eigenvalues of omega squared. So this exponential is simply e to the square root of our eigenvalues squared times z. And that runs down the diagonal. Okay, so back to our solution. Now we have expressions for these matrix exponentials in terms of the eigenvectors and eigenvalues of omega squared. So we substitute those in for our exponentials and we end up here. Just like we did for the transfer matrix method, we have a big ugly square matrix of numbers multiplying a column vector of unknowns. It's our initial values, but rather than keep doing this math, we will combine this into a single column vector of unknowns that we'll call our mode coefficients. And we'll do the same thing for the backward waves. Now we can write our solution this way. Just remember these mode coefficients is the eigenvector matrix backward dividing the initial conditions. We also need a solution for the magnetic fields. And following what we talked about in the transfer matrix method, this should not be a surprise, but we write the solution for our magnetic fields in a similar way. And since these mode coefficients are yet to be calculated, we can arbitrarily just stick a negative sign here, and we do this for convenience in order to calculate the v's from the w's. The way we do that is we'll differentiate this equation and we end up here. So now the negative sign from this lambda cancels with that lambda sign, so the derivative sign has no negatives, which is why we included it there. Now we can compare this to one of the original two equations that we calculated the wave equation from and figure out expressions for v. So remember, the derivatives of the u's was q times s. And the s's are, the solution for the s's are expressed in terms of the eigenvectors and the eigenvalues. Well, in the last slide, we took the derivative of the u's and we ended up with this expression. Well, we also have the derivative of the u's from this equation is q times s, or q times the solution that we have. So this is q times our solution, and these are both the derivative of the u's. Well, if we compare these, we see that v times lambda equals q times w. And if we solve this for v, the eigenvectors for the magnetic fields, we get q times w divided by lambda. And those are all matrices, square matrices. So here's our overall field solution. We have our s's written in terms of the w's and the exponentials, and we have our u's written in terms of the v's and our exponentials. And we can calculate v from w and q and lambda this way. Well, we can pull all this together into a single matrix equation, which should look very familiar. And now we have s's and u's all together, and we'll call that psi. So this psi parameter is all of our fields collected together into a single column vector. Here's all of our eigenvectors. Here's our eigenvalues describing propagation. The eigenvectors describes what the modes look like. Here's how they propagate. And here describes how much power is in each one of the modes. Those are our mode coefficients. So here's a breakdown of what I just said in words. The psi is the overall solution. These are the things we can look at and see our fields. The W is our eigenvector matrix, and these describe what the modes look like. These are the relative amplitudes of all of the different field components. This exponential, this becomes a diagonal matrix, which really describes how the eigenmodes propagate, how they accumulate phase. If there's loss, they decay, or if they're evanescent, they decay. If there's any gain, they might grow. And we also have the mode coefficients. This just tells us what the mode looks like and how they propagate. The mode coefficients tells us how much power is in each one of those modes, because we could selectively excite them if we wanted to. So here's how I envision this happening with a semi-analytical method. We have a number of different modes, and we'll probably have several hundred of these for a fully three-dimensional problem. If we look at one, take this, it's the first order mode probably. We have a column vector, which is its eigenvector. This first one describes the electric field components. The second one describes the magnetic field components, and it has some mode coefficient multiplying it. And the plus superscript means it's forward propagating, going from top to down. And this exponential e to the lambda 1 describes how that propagates, how it accumulates phase, or if it decays, or if it grows. And so the W and V's we could plot and we could see the field. The amplitude of this is described by C. And then, of course, how it propagates is the exponential. So when we analyze the cross-section of this, we calculate all possible modes that could exist in the cross-section. So here we're plotting all possible modes. I'm only drawing 5, and in practice we'll calculate many more than this. But all of those add up to give us what the overall field looks like. But each one of these modes propagates independently. They propagate at different speeds. So if we looked at the overall field and the interference amongst those, it looks crazy. But really all that's happening is those modes are just propagating independently, but at slightly different speeds. Well, we have these same exact modes traveling also backwards. So we have different mode coefficients because the backward traveling first order mode could have a different amplitude than the forward propagating fundamental mode. But it's all the same modes, but they're traveling backwards. And they also have their exponential now with a negative sign because they're traveling backward. So this is best as I can draw what these modes look like and how they correlate to the math. Okay, so let's talk about now when we have multiple layers. Everything we've done up to now was as if Maxwell's equations were inside this single Z uniform media, that it's of infinite extent in the Z direction but extruded with arbitrary complexity in the X and Y directions, which we Fourier transformed. Well, we know real devices aren't infinite in the Z direction, so we can describe any device as a series of slices, and each layer now is uniform in the Z direction. We need to be able to connect these together. So in fact, we're going to do this just like we did for the transfer matrix method and use scattering matrices. So what we're drawing here is a device that we may want to model, and it has 3 layers. So the first thing we'll do is we'll pull out a unit cell of this device. Now, one restriction of rigorous coupled wave analysis is that the period of each layer has to be the same. Now, this isn't strictly true, and there's some weird things that can be done. Sometimes we can even rotate the orientation of the layers. But for anything we're going to do now, we'll just assume it's the same period all the way through. I only point that out in case you come across something strange where there are different periods on different layers. There are ways to handle that in many cases. But for right now, it's the same periodicity all the way through each layer. So each layer has its own thickness. So we'll be at position 0 at the top. If the first layer has thickness Z1, we'll be at position Z1. I'll be at position Z2, Z3, etc. And we're assuming infinitely periodic in both the X and Y directions. So here's our geometry. Each layer has its own set of eigenmodes. So inside each layer, layer 1 will calculate its own P, its own Q. It'll have its own omega squared then, its own W and lambda and V, and also their own mode coefficients. And so we have these layer parameters for every single layer in our problem. And we will connect the layers with boundary conditions. These parameters, P, Q, lambda squared, and particularly W, V, and lambda, let us propagate those modes analytically within each layer, but we match the boundary conditions to connect all the layers together. So we'll go back, we will use the exact same type of scattering matrices that we did for transfer matrix method, and you should recognize the math. In fact, I've just copy and pasted this slide without any changes to it. So we have the overall field solution in some intermediate layer, and medium 1 and medium 2 right now are not layers. We have sandwiched a layer between 2 semi-infinite media, so they go off to infinity. And we'll calculate a scattering matrix associated with this. Now eventually we will turn medium 1 and medium 2 into just air, but we need to derive these equations because we also have our reflection and transmission connection scattering matrices to calculate. So anyway, here's the field inside the ith layer. That shouldn't be any surprise. The boundary conditions at the first interface will match the fields in medium 1 to the fields in layer 1, but right at the interface. So here's how we do that. This is exactly the same as with transfer matrix method. We do the same thing at the second interface. So these equations also look exactly like they did for transfer matrix method. So given those, we can derive all our equations to calculate the scattering matrices. That does not change at all, and in fact you derive that yourself in a homework. For buried layers, we have free space on the outside, and we have the exact same equations for calculating scattering matrices of buried layers when we have free space on the outside. Remember, this makes our scattering matrices symmetric, so we really only need to calculate 2 parameters. It also lets us interchange our layers arbitrarily when that becomes advantageous. So we want to calculate the global scattering matrix. Our terminology, we call our device scattering matrix when we've connected all the different layer scattering matrices together. In practice, when you're writing your code, we'll probably just always call this the global scattering matrix, and we slowly build it. But here we'll call the device scattering matrix when we've just connected all the layers together, and now we have the device sitting in free space, which may or may not be reality. So in order to make it reality, we'll take this device scattering matrix we just calculated after iterating through all the layers, and we'll star product with the reflection connection scattering matrix and the transmission connecting scattering matrix. And this follows exactly what we did in lecture 5. Now we have the global scattering matrix. Now we can calculate transmitted and reflected fields. This was copy and pasted from the transfer matrix method, but this is how we calculate the reflection and transmission region scattering matrices. Nothing's different here. When we calculate transmittance and reflectance, things change slightly here. The high-level equations don't, but how we define the source and things definitely do. So first, we need the incident field. And remember, this is not the field directly. These are amplitudes of our spatial harmonics. So we still have our x and y polarization components. There's also a z component, but we don't use that here. We're going to come up with a column vector using the delta function. And this will be a column vector of all zeros, but we're going to place a 1 in one particular position. Usually that's the center value corresponding to the zero order mode, but does not have to. Wherever the 1 is, that's what we're exciting our device with. So it makes sense, let's make that the zero order mode. So that's our delta function, and given the delta function, we can calculate the fields, this S column vector given the delta function and our 2 polarization vectors. And we calculate these using the same procedures that we did for the transfer matrix method. Now once we know these fields, remember our scattering matrices are relating the mode coefficients, not the fields directly. So we can calculate these mode coefficients by saying W backward divide S. And since this is the incident wave, it's at the top of the device in the reflection region, so we're using the Eigen vectors in the reflection region. Well, then we go to this global scattering matrix that we just constructed. We went through all the layers, we connected it to our reflection and transmission region, and we calculate the mode coefficients of the reflected and transmitted field. So this hasn't changed from the transfer matrix method. Well, given those, we can calculate the S's, or the electric field components, of the reflected and transmitted fields. So we're just going to write that as RT and TT. So these are column vectors, reflected fields, and transmitted fields. So those are the fields above and below the device, but right up against the edges, but inside those external regions. We only have the transverse components. We only have S sub x, S sub y, and ux and uy. We need to calculate sz and uz. So we can calculate those longitudinal components in the reflection and transmission regions from the parameters that we already have. We already have Rx and Ry, and of course we already have Kx and Ky. They're constant throughout the entire device. And we also have now a diagonal matrix, which is the Z components in the reflection region. And this equation will give us a column vector of the Z components, or S sub Z, in the reflection region, and a very similar equation for the transmission region. So this is S sub z on the transmitted side that we're just calling TZ now. And so here's a little derivation. It comes from the divergence condition. So we start off with del dot E equals 0. We expand to here. Now we transform to Fourier space, eliminate the minus j's, convert to matrix form, and solve for S sub z. And this is our general equation, and we just reuse this expression for RZ and TZ. Now we'll calculate diffraction efficiencies. So how I visualize it is on the right. We have a column vector now of column vectors, which contains the x, y, and z components. And we have another column vector of column vectors containing the x, y, z components on the transmitted side. We're going to convert these now to a big R and a big T, which will be the diffraction efficiencies of all of the modes on the reflected and transmitted sides. So first of all, the amplitude of these vectors is calculated very simply. And now we're ready to calculate the diffraction efficiencies of all the reflected modes. This equation should not surprise you. And on the transmitted side, this equation should not stop you. Notice we've taken this form. Instead of having the ratio of the epsilons, it's the ratio of the mu's. That's because we're calculating this from electric field quantities. So that's why the mu's are there. And don't forget, these are column vectors. We'll need to reshape those back to a two-dimensional array if you want to make it look kind of like these diffracted modes. Like you could lay that array right down on top of those and see how much energy or power is in each one of those modes. So that's it for the formulation of rigorous coupled wave analysis. Keep in mind we haven't talked about how it will be implemented. Hopefully in the formulation that some of that is obvious, and also coming from how you did transfer matrix method, we will be able to copy and paste our code with very, very few changes. But I wanted to also step you through the enhanced transmittance matrix approach. We won't implement that here, but I did want you to see it, because if speed ever becomes a necessity and not so much memory as a problem, this is a great, great approach. So I'll hopefully explain here the drawbacks and the benefits of it. In my experience, it's 5 to 10 times faster than using scattering matrices. So I'll say maybe 10 times. There is a drawback of the enhanced transmittance matrix. What we'll do is we will start at the very last layer of the device and work backward through the layers all the way up to the first layer. But we're storing parameters along the way. So if you have a lot of layers and you're storing parameters, you could run out of memory. Once we work backward, then we work forward, and then we can finally calculate reflectance and transmittance. But the fact that we have to work backward and store data before we work forward means we could run into some memory problems. But it is much faster if you don't run out of memory. So remember here, we have these two x matrices, which are our exponentials. This one, without the negative sign, is the bad one. This is the one that, if we use, will explode on us, particularly when there's evanescent fields or something like that. So the enhanced transmittance matrix method was the first developed to handle this. So essentially, we need to come up with a way to calculate reflectance and transmittance without using that particular x matrix. So we can write equations for our boundary conditions at a few different places. We have our first interface, which we can write this way. We have at some intermediate interface and some last interface. So what I would suggest to do, I won't do it here, but go back to, there was an earlier slide in this lecture where we showed boundary conditions that we use for the scattering matrices. Look at that, look at this, and try to reconcile that we really are talking about the same thing. So we have a boundary condition problem at the first interface, intermediate, and last interface, and right now our two unknowns are the reflected fields and the transmitted fields. So we want to calculate those without using that inverted x. So now we're going to work backwards through the layers. And we start at the very last interface, and recall this was our equation for that. Now what we'll do is we'll solve this equation for the mode coefficients. And we get this equation. Now what we're going to do is take this f backward divide b, and we're going to lump that into this other matrix that has some top part that we'll call a sub n and some bottom part we'll call b sub n. So these two parts is just f backward divide b. So we'll do this calculation and then extract a and b from that. Now we're going to define an intermediate transmittance matrix, and we'll define it this way. We're actually defining t sub n here. They're both unknown, but we're going to define it this way. So we're going to lump all of these expressions that were t and define t sub n this way. Now we can write our last equation this way. So the last equation we had on the previous slide can now be written this way in terms of this t sub n. Now notice, after doing this, our x is no longer inverted because we put an x in here that canceled with it, and now we just have a nice stable x in the denominator. So this is an expression for the mode coefficients in the last layer now. Now we need to look at the boundary condition for the second to last interface as we work backwards. Here's the equation. But we now have an expression for c sub n. So in fact we can put that in there, and here it is. That was our expression for c sub n. Well, now we can solve this big ugly matrix equation for c sub n minus 1. These are the mode coefficients now in the second to last layer. So here we do that. Well, notice now we have this big inverted x matrix, which is an unstable matrix. So hopefully what we do fixes this. So now we want to lump this f backward divide f with this matrix and this matrix. So all this stuff together we're going to lump together and call that another a over b, but now it's for the n minus 1 layer. So we can write a and b sub n minus 1 this way. That reduces our equation for the mode coefficients into the second to last layer this way. Remember, we put an x in our definition of t sub n, or I'm sorry, a definition now of t sub n minus 1, so this x dropped out and we just have one x in the denominator now. I'm sorry, not the denominator, but the second or the bottom half of this big matrix. And that is stable. But this t n minus 1 is still unknown. So we get the pattern. We keep going backwards. We keep calculating a new a and b, and then a new transmittance matrix comes out of that. And eventually, we get to the first interface. And we go to our equation we had for the very first interface, and we end up with this. Well, we can solve this now for r and t. We have an equation with r and t. This is a block matrix equation, so it actually represents two matrix equations. We have two equations, two unknowns. We can solve this for r and t1. So this is not the final t. These are transmittance parameters in the first layer which don't have any meaning right now. But we can solve this for r and t, and we do that. Now we have to work forward. Well, we can calculate t2 from our value of t1. We can calculate t3 from now our value of t2, and so on, until finally we calculate the t, or the electric field components on the transmitted side, from t sub n. So we went backwards, storing a bunch of parameters, and then we worked forward. Once we have r and t, those r and t's, remember, only contain the transverse components. They have x and y components. So we calculate the z components using those matrix equations, and then we calculate the diffraction efficiencies. So really this doesn't change once we have r and t, which initially only contains the transverse components. So these equations don't change from how we did it with scattering matrices. It shouldn't be a surprise.